So we've seen in the first 2 days 2 conjectures, right? The threesome conjecture, the APSP conjecture, which are very nice and maybe also very easy to state. Today we'll move on to like the biggest conjecture, SETH, which is about satisfiability. But maybe because it, first of all, is even more fundamental than the others, and second, because it's a tiny little bit harder to understand what the conjecture is actually about. This time we're going to do it differently. This time, in the first lecture, we'll start talking about algorithms for SAT. And in the meantime, like over the course of that, maybe we'll see why it is reasonable to conjecture hardness of SAT. Also, I think, very conceptually, it is a good experience to try and work on algorithms before you conjecture something is hard. That's maybe how you also would do it in real life. Okay. So let's quickly recap some of the basics of SAT. So I'm kind of assuming that you all have seen this before, so let's just be real quick, right? So whenever we talk about a satisfiability problem, you typically have some variables, x1 through xn. So throughout, I'm trying to denote the number of variables by capital N. An assignment is just a binary assignment to every variable, so you can view it as like a vector, as a bit vector of length n. Then a literal is either a variable or the negation of a variable. A clause is a disjunction of literals, and a formula, or a KCNF, then is, sorry, that's completely wrong, is a conjunction of clauses. Okay. So for some assignment, we say that a literal is satisfied, well, if it's a variable, it's satisfied if the assignment sets the variable to 1. If it's the negation of a variable, it's satisfied if the assignment sets the variable to 0. A clause is satisfied if at least some of its literals is satisfied. And a KCNF is satisfied if all of its clauses are satisfied. Okay? So far, so good. So I don't know, maybe, not sure whether it's necessary, but yeah. Like an example would be something like x1 or x2, and not x1 or not x2, which is indeed a satisfiable formula because you could set, let's say, x1 to 1 and x2 to 0. Okay? So let's talk about KSAT. KSAT is this super fundamental problem, right? As an input, you get a KCNF formula. Let's say with n variables, and with m clauses. And as the output, you should check whether that formula is satisfiable. Or in other words, is there a satisfying assignment for phi? Good. Now, whenever you think about KSAT, probably you think about the classical NP hardness theory, right? When the main result maybe there is to say that KSAT or even 3SAT is an NP-complete problem, which basically means it's equivalent to show that 3SAT can be solved in polynomial time to showing that all problems in NP can be solved in polynomial time. So in other words, the big hypothesis, which hopefully everyone believes in, right, is that P not equal to NP can be equivalently stated as 3SAT is not in time poly n. Right? Okay. Now, of course, as always, this is a very coarse-grained point of view. And what we'll do in this lecture is that we'll actually try to develop some algorithms which, maybe even refute this. Obviously, they won't. But let's see how far we can get. OK? So, right, what's the trivial algorithm for SAT? Okay, I heard a bunch of answers. I think some said exhaustive search. That's just 2 to the n. It's basically that, right? Trivial algorithm is you just try all assignments. Try all assignments, which leads to time, well, something like 2 to the n. Maybe one should be a little bit careful, right? Because we actually have to implement it. Maybe it's time 2 to the n times poly n. Because you actually have to test whether the formula is satisfied or something. OK. And now we'll try to develop better algorithms. So maybe you could quickly show me who has actually seen non-trivial SAT algorithms before. OK. I'll try to exclude you guys then. So what would you guess? How would, let's say, a very naive idea, how could a very naive idea look like which gives you an algorithm which gets a running time better than 2 to the n for SAT? Just give me some ideas. Didn't you say you have really seen some? I guess, like, as a very general method, that is not a bad idea. Let's say branching. How would you branch?
When we are sure that we cannot satisfy, for example, 2 clauses, we do not try to go to satisfy other ones. It is a no.
You mean, like, basically you try to enumerate all assignments, but as soon as you notice that the formula is unsatisfiable, you stop. That is, of course, a very good improvement. And I think in practice, this is exactly what people do. I mean, among like a billion other heuristics to get better algorithms. It will not lead to a faster theoretical algorithm, though. But still, branching is a good idea. Yes?
So maybe like the example on the board, if there is some clause that it appears as a literal or indicated literal in different clauses, that we can exclude those variables.
Nice. So what you're describing is like the basic idea of something which is called resolution, where you try to put different clauses together when you know that, when putting together, it excludes some assignment. Like, for instance, when you know that one clause says something like either x1 is true, then this must be true, or x2 is false, then something else must be true, then you can put them together. That does lead to better, let's say it does lead to algorithms. It's not as easy to analyze whether they actually get theoretical improvements in the end. But this is maybe the most promising direction for like the state-of-the-art algorithms. Like, at least they use something like resolution in them. But let's stick to like the branching algorithm. Can you see a very simple approach to an algorithm which would perform better than 2 to the n? Yes?
So half of the variables, so we assign all the segments with half of the algorithms and calculate clauses, and later half of the variables and save all the results and calculate like root time.
OK, so correct me if I understand this the wrong way, but what you're saying is first fix half of the variables by brute force for any assignment. For each fixed assignment, maybe you have already eliminated some clauses, and they give you like fixed answers for some of the variables. Is that what you were saying? OK. I think that might actually lead to something if you do it the right way, maybe if you throw in some randomization in there. Let's try even easier. Focus on one clause. Yes?
So find an unsatisfied clause.
Yes?
And then randomly set one of the literals.
Ooh, that's a very advanced idea. OK, keep that in mind. I'm going to come back to you at some point. Let's say, even easier. You have a clause. You want to satisfy that clause. Well, you could try all options of testing the variables. Is that really smart?
Just set one of the literals that are true.
OK, good. So in particular, let me rephrase it a little bit. Well, we will try all satisfying assignments of that clause. But we will not try one which is unsatisfying. That's stupid. Right? So maybe the first approach would be to say, you take an arbitrary clause. Let's say it has the form L1 or L2 or L3. Now, how many assignments are there which could satisfy that clause? 7, exactly. So what we do is we try all 7 satisfying assignments. That satisfy C. And then, well, this always sets 3 of the variables, or 3 of the literals, which in turn sets 3 of the variables. So now you recur in the rest. OK. I claim this follows the following running time. Running time of this algorithm, with n inputs, capital N inputs. Well, I claim this has the form you have 7 recursive calls, each on n minus 3 variables, plus some polynomial override. Can anyone see what this running time solves to?
7 power n by 3.
Sorry?
7 power n by 3.
7 power n by 3. Exactly, yes. Good. Let me write it down, and then I think, there you go. Are you convinced? One way to see this is just formally prove it by induction. Maybe the way which makes sense is basically, well, you group the variables into blocks of size 3, right? And we go through them, and every time we do not have 8 recursive calls, but we have 7 recursive calls. And well, if you work this out, which I guess I did yesterday, okay, this becomes 1.913 to the n. So this indeed is a much better algorithm than brute force. Even like if you want to sell it, you would even call it an exponential improvement over brute force. It's faster by an exponential factor. Right? OK, so we can do something non-trivial. Let's try more. Do you see a way of improving this algorithm a little bit? Let's stick to the same framework. Let's, for now, stick to the framework where you take one clause and you do something with its satisfying assignments and you recur. We'll do some smart stuff later, but just for this. Can you see some kind of optimization of this algorithm?
For each assignment you try, it's pretty easy to determine if it unsatisfies any of the other clauses. OK.
That probably leads to, again, like fast algorithms in practice, but this is always a little bit hard to analyze in the end. Let's try to stick for one clause for now. Later, I guess we'll get to more advanced methods. Though I don't think anything which considers 2 clauses at the same time. Yes?
Can't we solve this by not n? Like, what is the relation between n and n? So we can set one of the literals and go to next clause and do it. So we don't have to set all of the literals.
Good. Very nice. That's a very good insight. So I think that's already also what you were saying in the first place. So I kind of pushed you in the direction of setting all of them. But yes, we don't have to set all of them as long as we set one of them to be satisfying. So what could we do? Well, we could have 3 recursive calls, each of which sets like either L1 is true, or L2 is true, or L3 is true. Turns out that's not much better. But let's optimize that idea a tiny little bit more, and we get something better. Maybe instead of guessing which is a satisfying literal in this class, what instead should we guess? It's a little bit tricky to get the idea. So maybe I'll give you like 20 more seconds or something. I'm going to tell you. Any ideas? No ideas? OK. So here's another idea. Well, we want to guess one satisfying literal, but let's not guess an arbitrary one. Let's guess the first satisfying literal in the clause. There's only three options. Either L1 is satisfying, or L2 is satisfying and L1 is not satisfying, or L3 is satisfied and the other two are not. Okay? So the algorithm is like this. You still take an arbitrary clause. Again, let's call it L1 or L2 or L3. Now you guess the first satisfied literal. Okay, so well, I guess it's sufficient to write that down. What is the recurrence I have to write here? Very nice. Do you agree? Basically, right, if it's the first one, the first literal is satisfying, well, we only said this one. So we have one recursive call where we still have n-1 variables. The second one was the first satisfied literal. Then we can set two. We can set the first one to false, the second one to true. So we recur on only n-2 variables. Same for the third. OK? This sort of recurrence relation to know where you have several calls with like n-1, n-2, whatever, they appear pretty frequent in the design of exponential time algorithms. And the trick to analyze them typically is just you claim by induction that you prove some upper bound. OK, so let's claim by induction that we prove that T of n is at most, let's say, alpha to the n times poly n. Oh yeah, the poly is annoying. Of course, forgot to write it. Of course, you still have a polynomial overhead. OK, let's claim you have this by induction. Then, well, I guess I should leave this. Keep that in mind. I'm going to jump to the other board. Right? Now, if you have a look over there to the recurrence relation, and if you just imagine that T of n has the form alpha to the n, then this is basically equivalent to saying that alpha to the n is at most alpha to the n-1 plus alpha to the n-2 plus alpha to the n-3. Right? Which if I now take out, like basically I take out alpha to the n-3 on both sides, just becomes that alpha cubed is at most alpha squared plus alpha plus 1. Okay, and maybe you should take the alpha which actually which achieves equality here. So then this just becomes some sort of polynomial equation which you can solve. Okay, and in particular, what turns out you can choose. Let me maybe pick orange to see that this is the solution. We can pick alpha to be 1.840. So in particular, we get an algorithm with a running time of 1.840 to the n times poly n. Great. More progress. And this is how you play this game. You know, you find some improvement. The improvement typically is an observation about set, about case set in this case, right? You've noticed that clauses are not, like, have some kind of weakness which you can exploit. In the first algorithm we just exploited, well, they have only 7 satisfying assignments, not 8 of them. That's a weakness. You can exploit it by just enumerating the 7. then you observe, actually, it's not that they have 7 arbitrary assignments, but actually you can always assume basically that they have a first satisfying variable. That's another weakness you can exploit. So in general, if you think about the SAT problem, the K-SAT problem, no, actually, if you think about the SAT problem, not only for KC and F formulas, but for arbitrary formulas, or for arbitrary circuits, this problem is still well defined. I give you an arbitrary obscure circuit, you have to check whether there is a satisfying input, like a satisfying assignment to the variable such that the circuit evaluates to 1. And it's very natural to see that actually the more complicated the circuit class becomes, the less likely it's to get algorithms fastened to the n. In particular, if you think about like an oracle or like a black box circuit, you would not expect any improvement. Actually, easy to show that if you have a black box circuit, something which you can literally not look into, 2 to the n is the best you can do. Right, and now what we're trying to do is we really try to look into the circuit and try to exploit the weaknesses of it. This was, of course, so far a very easy approach. Now, I decided to spend some more time and show you, in detail at least a little bit, one more complicated algorithm for SAT. And this is very related to what you've been saying before. Actually, let me also put a reference here, because I forgot. So this algorithm is due to Monian and Speckenmeyer from '85. So what we'll do next is another algorithm, famous algorithm for SAT, which is called Schöning's random walk algorithm. Who of you have seen that before? Okay, some. Good. So maybe let's try to push the idea to the extreme. Like we have already observed, whenever you have a clause which is not satisfied, well, you should switch it to like a satisfying assignment. In particular, you should not consider the falsifying assignments of a clause. Now Schöning came up with this algorithm. Let's say you start with a uniformly random assignment. And then let's repeat the following thing. Let's say 3n times that number is going to make sense at some point. 3n times, we test, well, if alpha is satisfying, perfect, we're done. Otherwise, take an unsatisfied clause. Let me again denote it by C, literals L1, L2, or L3. And what should we do with it? You already said at the beginning. Sorry, you said flip?
Flip the way it is.
Which one?
You can pick an arbitrary one.
Good. Yes? So, perfect, at random, exactly. So Schöning's algorithm basically says randomly flip either L1 or L2 or L3 in alpha. Yes. Should I repeat this?
No, that's okay.
Okay, I'll give him a minute. Okay. Okay, is the algorithm clear? In particular, with every step, we will definitely set, like whenever we take an unsatisfied clause, right, we will definitely satisfy the clause afterwards. Now the hope is, whenever, okay, suppose you're in some assignment alpha. How does alpha differ from a satisfying assignment, or from, let's say, the optimal assignment? Well, clearly, it differs in either L1, L2, or L3 from the optimal assignment. Because the optimal one, like the satisfying one, has to satisfy this clause. So the hope is that in this step, we pick the right one. So we pick whatever is the flip which brings us closer to the satisfying assignment, which happens with probability 1/3. Of course, it's not particularly large, but it is something non-trivial. And let's see how we can exploit that. OK. So another way to view this, basically, or another very intuitive way to see it is, well, if you think of the space of assignments of the formula, then this algorithm does something like a random walk in the space. And you start random, and then you just walk in random directions. But it's not uniformly random. It is a walk which is biased towards satisfying the clauses in the instance. So we're not doing a stupid thing. We're really exploiting the circuit here with the satisfiability formula to get closer to satisfying assignment. Yes?
Why it becomes nearer to the satisfied one? Because when we flip something, maybe another clause becomes.
You're right. Like, it could happen. Well, OK, the thing I'm trying to say is, like, there is a good choice, right? With one of those, you get closer to the satisfying assignment. But with two other choices, you get further away. That's absolutely correct. That is going to happen. But if you flip the right one, let's say, in the satisfying assignment, you have to flip L1. Then you have to change it, even though L1 might falsify some other clauses. Because anyways, that's the only way to get to the satisfying assignment in the end. OK. So here is a very, very cute analysis. It's extremely simple. Yes?
And if it is unsatisfiable at all, after how many steps?
Good. Yes, perfect. This is not a complete algorithm. This is going to fail, or let's see what the analysis gives us. Then I'm going to add a line there. Perfect. OK. So for the analysis, let me define something. Let's say, let me call the distance d is the Hamming distance from the initial alpha alpha to a satisfying assignment. Hamming distance just means how many bits do I have to flip such that I reach the optimal assignment. OK? Here's the claim. Well, here's the claim. When d is our initial distance, like whatever, we execute the first line, we pick a random assignment. Then we know let's pretend we know the distance to the optimal assignment. Then the algorithm succeeds in that the algorithm finds a satisfying assignment. With probability at least 2 to the minus d. OK, that is obviously a terrible success probability. Even more? Sure. Can you read this, or should I repeat it? OK. Where's the sponge? Oh, over there. OK. So the success probability of the algorithm is 2 to the minus d. This is the claim. And here's the proof. So let me model the distance from the current satisfying assignment to an optimal satisfying assignment as follows. You can basically view it as like this random walk. In the beginning, the distance is d. And then in every step, you either increase the distance to the satisfying assignment, or you decrease the distance to the satisfying assignment. Both can happen with a certain probability. Namely, you increase the distance if you pick the wrong literals, which happens with probability 2/3. And you can decrease the distance if you pick the right literal, happens with probability 1/3. Not exactly accurate. Of course, it could happen that you have two literals which you have to change. Then actually you get higher success probabilities. But in the worst case, this is the probabilities. Let me pretend we're in the worst case. So then you have this kind of random walk, right? And somewhere in this random walk, there's 0. Like 1, and then maybe you have 0. And still, the same thing happens. Like at some point, you might reach 0th probability. 1/3 from 1. And it's a little bit stupid, but let me also pretend like there is like there's a -1. And that you can even continue in this direction. So this is actually we would have to introduce like a special case for 0, and then analyze a random walk which stops somewhere. Let me make it even worse and pretend like you could even get negative. That was kind of bad for us even, and say the probability, even in this worsened random walk, that we reach 0, which is what we want at the end, will be somewhat decent. Yes?
Yeah. How did you get 2/3
OK, so let's say you start at D, right? This is like the initial assignment. And you take an unsatisfied clause. Since it's unsatisfied, this clause, or the assignment alpha, differs from the optimal assignment in either L1, L2, or L3. Now, which means that there's at least one literal which, when I flip it, I move closer to the satisfying assignment. So this I pick with probability 1/3. With probability 2/3, I might go in the other direction. This is only true, however, if there's exactly one literal. It might even be beneficial for you that there's maybe 2 or even all 3 of them. You have to flip them. Then, of course, with higher probability, you should move in this direction. So this random walk real model is like the worst case scenario. This is the worst which can happen to you.
What do you mean that the algorithm fails?
As in, it does not, I guess, imagine that the algorithm, when you find SUD, then you return SUD, and at the end, you just say unsud. So the algorithm succeeds. Like, maybe let's pretend for a minute just that the instance which you are given is satisfiable. Then by succeeds, I mean the algorithm finds a satisfying assignment. OK, the time, just whatever it takes to run this once, which I guess is just polynomial time, right? It will never get stuck.
So the probability of success is always
Sorry?
the probability of success is always 1.
No, you only repeat this 3n times, right?
So that means that it might return unsatisfiable?
Well, let's say as soon as it reached the end, you just say it failed for now.
Okay.
OK? Now,
Excuse me.
yes.
Is it possible that in these 3 states, it see one state a couple of times or get stuck in a circle?
Absolutely possible. It might happen that you move closer to the satisfying assignment, but then you flip a wrong literal. You move closer and you flip a wrong. Might happen. Let me get to the analysis of this. Then I think it's going to get clearer. I wanted to draw the picture first. So for the analysis of this, consider the following calculation. So the probability that the algorithm succeeds is basically the probability that the algorithm finds a satisfying assignment in 3 n steps, and at most 3 n steps. Right? Because that's what the algorithm does. It repeats something for 3 n steps. So let me say this probability is at least the probability that the algorithm finds a satisfying assignment in exactly 3D steps. That's obviously, That's obviously a sub-event in a sense. Like if you manage to find a satisfying assignment in most 3n steps, well, then it's sufficient to just lower bound the probability that you find it in exactly 3D steps. Right? And now I'm making the situation even worse. But now, finding a satisfying assignment in exactly 3D steps, what does it mean? It means you start in this random walk. You walk for 3D steps, left, right, whatever, right? Now I want to say, what's the probability that at 3D steps you stop at 0? Right? If you stop at 0, you definitely found a satisfying assignment. So this is the probability that, well, after 3D steps you reach 0. In the random walk. At least that. So when after 3D steps you reach 0, I claim, first of all, well, the distance from d to 0 is d. If you reach it in exactly 3D steps, you must have taken 2D steps to the left and d steps to the right. That's the only way in which you can reach 0. Right? Yeah, let me write it like this. Okay. Yes. Sorry, yes. This is, by this I mean irrespective of the order. In total, you took 2d steps to the left and d steps to the right, not necessarily that order. Okay, can you tell me what's the probability that this event happens? What was that? 1/3 to the 2d times what?
And then you need a binomial function.
Good. And times what was that?
2/3 to the d.
Yes. And what's the binomial coefficient? 3d choose d.
Can we assume that 3D is not greater than
Sorry?
Can we assume that 3D is not greater than
D is
d is
at most n.
at most n, yes. Because you start from like the distance, like d is the distance to the optimal assignment. I just erased it. But the distance obviously can be at most n because,
the 3D. Can we assume that 3D is 2D?
No. But we can, like, what the thing which is necessary is to assume that 3D is at most 3n, right? And that we have.
Yeah, but the probability is not exact, right? So you can't go d steps to the left first.
Oh, I see. Let's, good point. Yeah, let's make it even worse. Let's pretend this walk is infinite. Like this random walk does not model the scenario realistically at all, but we really only made it worse the entire time. We allowed it to be infinite to the left, infinite to the right. We made these probabilities strictly equal to 2/3. So it's just a way to model this in a worst case scenario. So then this is not going to bother us. It might just help us, right? If you reach the limit, you can, this might only make it worse. Okay, good. So now let me manipulate this a little bit, right? There's this fact that actually, really useful fact that n choose alpha is roughly the same as 1 over alpha to the alpha n times 1 minus 1 over alpha, 1 over 1 minus alpha to the 1 minus alpha n. Now if you use this here, let me not care about the inequality too much, then what you get is 3 to the d. Right, this is like it's like if you have 3d choose alpha times 3d, where alpha is 1/3. So you have 3 to the d times 1 minus 1 over alpha is 3/2. To the 1 minus alpha is 2/3 times 3d, right, which is 2d, times the stuff from before. And if you work this out, it turns out this is exactly 2 to the minus d. Basically because you have 3 to the d times 3 to the 2d divided by 3 to the 2d, divided by 3 to the d. So the 3's all cancel. What remains is 1 over 2 to the 2d times 2 to the d. So 1, 2 to the d remains in the denominator. Yes?
You consider that it is infinitely many steps to the right of it, and maybe it is worse than what we actually have.
Exactly.
Or maybe it is not tight, and in fact,
Yep, it's not tight. You could maybe analyze it slightly better, but like as far as I understand, you might get like slightly better bounds here, but it will not actually give you an asymptotic improvement of the algorithm. Yes?
Yeah, so maybe I'm confused, but it seems like 2 to the minus d is a very small number.
2 to the minus d is a very small number, absolutely. So this is a terrible algorithm. I agree.
Yeah, so it's like saying some probability is greater than some very small number is kind of...
Yes, yes, absolutely. So we're saying this algorithm will succeed with a very small number, but there's a trick. Whenever you have an algorithm which succeeds with probability 2 to the minus d, you should repeat the algorithm 2 to the d times. Now, it's not exactly clear what it means for us, but basically what you have to do is now you repeat this entire algorithm some number of times. If you haven't found a satisfying assignment in the end, you say answer.
Why we do not find L1 or L2 or L3 instead of randomly based on something? For example, we can check each of them and we see if we flip each of them how many satisfied clauses we will have and choose the one which we pass.
That is misleading. If you count the satisfying clauses, that's actually a very bad heuristic, because you could have a billion good assignments which satisfy all clauses except for one. But then you have one satisfying assignment which looks completely different and satisfies all clauses. So then you would always find these good-looking clauses without actually going close to the actual satisfying assignment.
We can use some randomness so that...
But it doesn't tell you anything about, like, they could be very far from each other in Hamming distance, unfortunately. So that is really weird. Like, it allows you to encode really weird structures. OK, so we're not exactly through yet with the analysis here. So let's do that. How often should we repeat this? There's a very simple answer, which is, how often would you repeat this now? Any guess? What was that?
2 to the n over 2.
2 to the n over 2. Excellent. Who said that, actually? Did you say that? You said it. Good. And what's the argument for 2 to the n over 2?
Random assignment is probably Hamming distance.
Good. So let's try one, first try. So let's repeat this. Well, observation is this. We have that the distance d is at most n half with probability half. Bigger?
Can you raise this board up?
Sure. Right? If I pick this random assignment at the beginning of the loop, with probability 1/2, it has distance at most n half. So then, let's say 100 times 2 to the n half, to the d, which is 100 times 2 to the n over 2. Repetitions suffice. Because then, each repetition succeeds with probability 2 to the minus d, which is 2 to the minus n half. You repeat it 2 to the n half times with good probability. There's one of them which succeeds, right? OK, so you get an algorithm in running time. Well, 2 to the n over 2 times poly n. And if you work it out, this turns out to be, this is basically just square root of 2, right? So this is 1.415 to the n times poly n, which already shows that the approach is pretty powerful. But let me spend one more equation to show you that you can actually analyze it better. You can actually get a better constant than root 2 in the base. So here's like an optimized version of analyzing this. I'm just going to put it here real quick. It doesn't really matter that much, but just to give you like a flavor. Well, actually, the probability that the entire algorithm succeeds, like not a single loop, you can model it as follows, right? It's like in every, that this part of the algorithm succeeds. Scratch the entire, it's just nonsense. I claim this expression. Right? First, you condition on the distance being something, let's say k. And if that's the case, the algorithm is going to succeed with probability 2 to the minus k. Right? Now, what's the probability that the distance is k to begin with? Well, that's just basically the number of Hamming distance k strings to an arbitrary string divided by 2 to the n. So that is n choose k divided by 2 to the n times 2 to the minus k. OK? Now, let's use effect, which is the binomial theorem. Which states that a plus b to the n can be expressed as this sum right? You've all seen it before. I'm just writing it here so that you can verify that this actually happens to be 1 over 2 to the n times half plus 1 to the n. Right? You pick a to be half. You pick b to be 1. Then half plus 1 to the n is just the sum of all k equals all the k, binomial coefficient times half to the k times 1 to the something. Good? And this happens to be 3/4. This is 3/2. This is 3/4 to the n. Right? So actually the entire success probability of the loop is not just 2 to the minus n half, but it's actually 3/4 to the n. So what you can put here in the end, then finally completes the algorithm, is this 4/3. Say 100 times 4/3 to the n. Maybe spend a little more time. Basically, well, if you repeat it 4/3 to the n many times, just one of them succeeds with constant probability. Each individual one succeeds with 3/4 to the n, right? So if you repeat it that often, you can work it out, and then it becomes a constant. If you repeat it 100 times that, then the probability boosts, and it becomes basically exponentially small that you fail even after that. Yes?
This might be related to that optimization, or maybe this is what you said doesn't really affect it, but isn't it like you're really doing a random walk on a finite graph?
Yes.
A path graph from 0 to
Yes.
n, and it's like something, couldn't you do something with like behaving time of such a walk?
I guess like a cleaner way, or like a way which is more in line with this field of math to analyze it would be that. But I don't think it actually gives you an improvement. I think people have actually tried, and 4/3 was what came out of this. I'm not sure. Maybe there's like some tiny improvements.
And you said how you got that 100?
I mean, like, okay, maybe just ignore the 100 for now. Like, I guess even like what I said before is also not entirely accurate. Actually, you would do it like poly n times to get the speed up I claim, but it's like you repeat it some number of times to get a higher success probability. This is all what I'm saying. I just put 100 there. Don't worry. Okay, I have to hurry up a little bit because I've spent more time with the algorithms than I expected. But here's the bottom line. We've seen a bunch of algorithms. Actually, let me give you at least like two more references just so that you can see them. Let me maybe erase this part. So this is not where the research stopped. You know, like there was a bunch of follow-up work, and this is still very, very active. Still very much open question. What is the fastest algorithm for SAT? Also, note that so far we only had a look at K-SAT, 3-SAT. Actually, we also care about K-SAT, so I also have to comment on that. But really, what happened is, you know, like, oops. If you have a look at what's known, then really you have these algorithms which perform somewhat well, but still very clearly exponential time, right? This is maybe the first. This was this Moni and Speckenmeyer. If you tune it a little bit, we've seen before. You could bring it down to something like this. This is like the branching-based techniques we saw in the beginning, algorithms 2 and 1, right? They could bring it down to something, not much further than that. So then people thought about different things. So what came out is like a different algorithm due to Schöning, which is based on local search. It's also a pretty famous algorithm. Maybe you've seen that one. And then there was the Schöning's algorithm, which we've just seen now, based on random walks. And now basically the modern approach is to use these resolution techniques, which one of you was hinting at in the beginning. So you try to have some sort of brute force algorithm, but you deduce the assignments of some variables by resolution. I guess this was in 97, and then it's a bunch of improvements. The PPZ and PPSZ algorithms are famous here. And then there was an improvement, and in the end, they got this running time. Doesn't matter. So this is resolution-based, or at least with the help of resolution. Bottom line is you have all these techniques, all these people working on this problem, and so much effort would went into that. Like the algorithms also became very complicated in the end. Just a second. And still, we're stuck at something like 1 to 308 to the n. Still, we're stuck at exponential time. So maybe this is exactly. Maybe this led people to believe, OK, maybe then 3-SAT really requires exponential time, which then led to the exponential time hypothesis. Let me write it down quickly, then I'm going to answer the question. So, which formally states that there is some constant delta such that 3-SAT cannot be solved in time 2 to the delta n. OK? So all these running times have this form, some causative constant delta, 2 to the z, right? The exponential time hypothesis states you can maybe bring this down to something, but you will not be able to reach an arbitrary number of zeros and a 1 here. This is not possible. There's a fixed limit to this. OK, you had a question?
Are the resolution techniques randomized or they're deterministic?
They're very highly randomized.
So like, is the partial deterministic the local search or?
No, so they actually, like, they're built on a different technique, which is very similar to what one of you suggested in the beginning. Like you fix some variables, but then you can use resolution to deduce the value of others. But you have to use randomness to say which variables do you fix first. Otherwise, it's hard to analyze. I don't know, sorry. I think maybe some of them.
Roughly the same.
Sorry? Roughly the same?
Roughly the same. As
Roughly the same. Okay.
Yeah, I think it's just Schöning's algorithm what it describes any complicated.
This one can be randomized. OK, I didn't know. Good. Do you mean the 4/3 to the end? OK. 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 So that's basically the story for 3-SAT. bottom line being, there is non-trivial algorithms. There's highly non-trivial algorithms, but maybe no sub-exponential time algorithms. So let's have a quick look at KSAT. And for KSAT, well, what do these techniques give us? The branching-based techniques, turns out, they lead to algorithms of the form, 2 to the 1 minus 1 over k times n. Maybe this is some constant c. Doesn't matter that much. So they do give you some non-trivial improvements, but the savings in the exponent become smaller and smaller with every k. And now you have all these other techniques. You have local search. We had the random walk approach. There was these resolution-based techniques. There's a method which I haven't written there because it actually does not give competitively well 3-set algorithms, but it's really important. It's called the polynomial method. Just I specifically want to highlight it because this is a method which is particularly, it's a fine-grained algorithms method if you want to view it that way. And all of these, and whatever we know, even those, in the best we can get so far is a running time of the form 2 to the minus 1 minus c over k times n. So that's better than before. The savings are bigger. But still, for large enough k, the savings vanish. So the takeaway from this is, even with all the algorithmic effort we put into there, for k going to infinity, we don't even have non-trivial algorithms. It just becomes brute force again. And that statement is the strong exponential time hypothesis. Formally, it says that for all constants epsilon, there is some k such that KSAT cannot be solved in time 2 to the 1 minus epsilon times n. Okay, that's exactly the intuition which I said before. For large enough k, you cannot beat brute force. In other words, for any improvement over brute force which you want to have, there is some k such that you cannot achieve it anymore. Okay, I'll give you some minutes to digest it, but let me note that the name strong exponential time hypothesis, it suggests that it should be a stronger hypothesis than the exponential time hypothesis, right? SETH should imply ETH. And that is in fact true, though not easy to see. So we put it as a bonus exercise. And by the way, maybe let me end the lecture by saying actually the TAs asked me to tell you, the bonus exercise on the sheet, they're really meant to be like bonuses. We do not expect at all that you can solve them in the same day as the lecture. So yeah, it's impressive if you manage to, but really we expected you not to be able to do that. So if it's a bonus exercise, don't feel bad about not solving it today. Good. So I'm going to stop here, and Amir is going to continue with the stuff in like 10 minutes. Let's say at 10:10.